Welcome to the presentation of our paper, Homography-Based Loss Function for Camera Pose Regression. This work introduces a novel loss function that defines the error between two camera poses in the context of visual-based relocalization. It was supported by Ifremer, the French Institute for Ocean Research, as well as Cosmer and Lys laboratories of Toulon University. Say we have visited a site of interest and acquired some images in the process. Later, we want to come back to this specific site and be able to localize ourselves in this environment. We must first define a reference frame in which we will localize ourselves. To address this, the first step in visual relocalization is to create a ground truth reference model based on the acquired images. There are several ways to achieve this. The most popular method is structure for motion, which recovers the camera poses along with the geometry of the scene. Other methods to obtain this reference include depth-based SLAM and, in rare examples, motion capture systems or gantry robots. Given this reference model, we want to retrieve the 6 degrees of freedom pose of a newly acquired image. In this presentation, poses will be represented with T and Q, where T is a translation component and Q a quaternion representing the rotation component. This problem has been tackled in numerous ways. There are traditional vision pipelines based on uncrafted features. But thanks to advances in deep learning, this task has benefited from replacing some of its parts with deep learning counterparts. In some approaches, poses are directly learned from input images in an end-to-end manner. In this work, we focus on PoseNet-like architecture, a straightforward CNN that takes as input an image and outputs its 6 degrees of freedom pose. In order to learn the correct pose, the network relies on a loss function that embeds how the predicted pose is different from the ground truth pose. Most existing loss functions struggle with the following problems. The rotation error does not always relate to any intuitive phenomena. The weighting between translation and rotation error is either arbitrary or difficult to tune, in addition to being the same for all images. Rotation and translation are not in the same space or group. Kendall et al. Overcome all aforementioned limitations by introducing their geometric reprojection error, which mimics the traditionally used reprojection error. It also has a particularly interesting property for visual relocalization. It minimizes the symmetric as structure for motion, hence it should achieve near-optimal performance when the reference model is generated using SFM. However, this loss presents some drawbacks for its direct application to deep learning. For example, in the initial state of the neural network, poses predictions are initialized around an arbitrary value that is often far from the ground truth, which means that some points can be projected to infinity or onto the backside of the image. In the first case, the loss is not differentiable. In the other case, back-projected points lead to a wide local minimum. In our work, we introduce a novel loss function that approximates the reprojection error while avoiding these drawbacks. The core idea is that we replace the observed 3D points by virtual planes parallel to the ground truth camera image plane. We then express our error directly in the homographies induced by these planes between the ground truth and the estimated pose. Let's focus on one of these planes. If the ground truth and estimated pose were superimposed, the homography induced by this plane between the two poses should be the identity matrix. Thus, for a given plane, we may quantify the error as the difference between this homography and the identity matrix. More specifically, we define the error for that plane as the squared Frobenius norm of the resulting difference matrix. Because the plane is parallel to the ground truth image plane, we fix the normal vector. We then integrate this error for all possible planes between two given boundaries, xmin and xmax, representing the observed scene. There is actually a closed-form solution to this integral. It depends only on the relative pose between the two cameras as well as the minimum and maximum distance of the observed scene and the normal vector to the plane. To motivate this loss function, we show that there is a connection between our loss and the reprojection error. Let P and P' be the respective projection of the same 3D point into the ground truth and estimated camera views. We can express the reprojection error as displayed. We can then express P' in terms of P using its homography. We notice that S tends toward 1 when the estimated pose tends toward the ground truth. By using the approximation S equals 1 and integrating all points on the tensor, we retrieve our single plane homography loss. This way, our homographic error will tend to the reprojection error when poses are close. We additionally demonstrate in the paper that the proposed loss function reaches its minimum if and only if poses are actually superimposed. Here, we show how minimizing the reprojection error affects the camera initialized looking in the opposite direction from the scene. The camera actually falls in the previously mentioned local minimum. In contrast, with the same initialization, the presented homography loss manages to flip the camera and converge to the ground truth. We report results of previously mentioned loss functions on the Cambridge landmarks and 7 scenes datasets. While the geometric reprojection error outperforms our loss on the SFM-based Cambridge landmark dataset, we achieve a better performance on the depth-based 7 scenes dataset. This is consistent with the claims of Brackman et al., who state that methods that optimize a similar cost function as a reference algorithm better replicate the local minima and imperfections of the pseudo-ground truth. Complete results are available in the paper. Thank you for your attention.